So let's start. Okay, have you guys seen this problem before?
Yes. It's at 3 p.m., right? On the 9th?
What's that?
Final exam?
Oh, it's at, for the final exam. So there are, some of you have your thermodynamics exam at 6:15 or 6. So for those guys, I sent a survey. So I think that 28 people who are giving it at 2:15, and I will let you know what room you got to come to give the exam. Okay, but you will not be allowed to leave before 3:30 because we don't want you to talk with the students who are taking the exam at a later time. So you'll be there from 2:15 to 3:30. You're free to leave after 3:30, but my feeling is you'll be there till 5:30. It's 4:45. 4:45 is when you finish, and then the rest of the class, I will let you know the room. You will be there from 3:15 to 5:45. Okay. I've always done this after the exam is over, after grading is done. I post the grades on Blackboard, and you can contest your grade. And it's going to be tricky this time because May 9th is the exam, and we end it in the night, and then we have 2 full days to finish grading and assigning grades, and it's like 200 exams. So I'm going to try to get it done by May 11th, and so then you can contest your grade on May 11th, the second half of the day, or maybe on May 12th, which is, the grades are due at 2 p.m. on May 12th, so we have to get the grades in. But you definitely will get a chance to contest your grade, ask for a regrade, not an issue. Okay? Okay, so have you guys seen this problem before? I had asked it in the tutorial. Okay, so the people who did not read this, do this problem. Let's do this because it's going to set up for the next problem, which is very similar. So the 5-pound cylinder, 5-pound cylinder is falling from A with a speed of 10 feet per second onto the platform. Determine the maximum displacement of the platform caused by the collision. The spring has an unstretched length of 1.75 feet and is originally kept in compression by the 1 foot long cables attached to the platform. Neglect the mass of the platform and spring and any energy lost during collision. Okay, so the key thing is, besides the fact that this cylinder is dropped from a height of 3 feet, what you got to know is that the unstretched length of the spring. So if you remove this thing here, the plate, then the spring is going to be 1.75 meters long, so 7.5 feet long. Okay, that's when the force in the spring is 0. So it's held in compression. Okay, the distance it's compressed is 0.75 feet. Okay, when this block is dropped on top of it, and it's assumed that, well, it's a massless platform, so there's no energy loss. But once it hits the platform, it sticks to the platform, and then the complete unit is compressed because it has momentum going downwards. Okay, so let's see, so the question is, what's the displacement? So let's say that this is y, that's the displacement of the spring, and you got to find what this displacement is. So what do I do? How do I go about solving this? So again, if you remember the whole the recipe I gave you, first you want to ask the question is it velocity as a function of distance? Is that what you're after? That's pretty much what you're after, right? You're given the velocity, and then the velocity is 0, and then initially the distance is 3 feet, and the velocity is 10 feet per second. So clearly you got to use either the conservation of energy or principle of work and energy. Okay, the simpler one is conservation. Can you use conservation of energy? We can use conservation of energy because there's no dissipative force, nor is there a non-conservative force. Again, friction is a non-conservative force. So conservation of energy is what we'll use. So T1 plus V1 equals T2 plus V2. Okay, so the initial energy is half mVA square okay. What else do we have for the potential? Initially there's only potential energy due to gravity, right? So that's going to be mg, and we got to choose a datum. So let's choose, I mean, it's up to you. You can choose this one, or I'll just choose this as the datum. That is well, you don't know what y is. So mg 3 plus y. So what about the sign? Is it right? Is the sign correct? Is it positive or negative? Negative. It's positive, right? Because when it is moved up, it has potential to do work, and that's positive. The final kinetic energy. Oh well, I forgot something. The initial potential. Sorry, the energy in the spring should also be a part of V1. So initially, there's half k times the displacement. So this is always the length of the spring minus the free length of the spring. So the length of the spring right now is 1 minus the free length of the spring is 1.75. Is the sign okay, or it should be negative? The potential energy of a spring is always positive. Okay, equals T2. What's the final kinetic energy? It's 0. Plus the final potential energy is going to be 0 because the datum is right at right over here. That's where we enter. So that's 0 plus the final potential energy due to the spring. So that's half k times so the net length of the spring is going to be what? 1 minus y minus 1.75, right? So 1 minus y because this length here is going to be 1 minus y. So then the length of the spring is this, and this is the free length. So L minus L0 square. Okay, so the velocity is known, mass is known. Okay, by the way, remember I told you that there won't be any question on feet LB. It turns out there is a question, or 2 questions on feet LB units. Okay, so please know how to solve problems when the units are pounds, feet. I don't like to put problems, but the other instructor likes to put questions. So, yeah. Yeah, if it's given like this, in this form, 5 lb, then it is 5 lb weight. That's how the book uses it. So, for example, in this case, m would be 5 divided by 32.2, and this would be 5. Okay. K is 400, not 4000. And I think the only unknown here is y, right? Everything else is known, so you can solve for y. You'll get a quadratic equation. So this is what I got: 200 y squared minus 295y minus 22.76 equal to 0. And one of the roots is going to probably be negative, I think, and that doesn't make sense. Y is positive, so or it'll be it won't be imaginary. Sorry, it will be negative. So the positive root is 0.0735 feet. Okay, is that clear? Any questions on this? Okay, so what I did next is I added a slight twist to the problem. Okay, the setup is the same, except that the platform now, this platform has a mass of 1 pound. Okay, so the block is falling on the platform, which is massy. It has 1 pound weight, sticks to the platform, and this whole unit is then compressed by the spring. You got to find the displacement of this. Same thing, but the platform has mass. So initial velocity is 10 feet per second, position is 3, final velocity is 0, the final displacement is unknown. Okay, now my question to you is, how do I go about solving this? So you see that there is, you're asked position velocity as a function of distance. So you're tempted to use, well, conservation of energy. Can you use conservation of energy? Why? So is energy conserved?
Well, we have to use that
Okay, so the previous problem what we did was we said energy over here is equal to the energy when the spring is compressed, right? Energy is conserved. So clearly when this mass is moving from that height to the platform, potential energy is converted to kinetic energy, and then this kinetic energy is going to be stored as spring energy as well as potential energy, of course. Now in this case, if the mass comes and hits the platform and sticks to it, what sort of collision is it? It's a plastic collision. E equals 0. So if there's a collision and if E is less than 1, energy is not conserved. You cannot use conservation of energy. So you cannot just say T1 V1 T1 plus V1 equals T2 plus V2. You'll have to actually analyze this by parts. So you got to look at the motion from top to before the mass from where it is dropped all the way till it's about to hit the platform. Okay, then when it's about to hit the platform, you got to use the conservation of momentum to find the new velocity, and then solve it again as a conservation of energy problem, because now there is no energy loss once this mass and platform have one speed. It's going to go under the, it's going to move under the influence of the spring, and there's no dissipation there. So
since it's plastic collision, at that after that, you can consider it a small
yeah. So conservation is, let me write it down. So what we'll do is we'll analyze this in 3 parts, okay? And this is where you see a mixture of 2 concepts. Here it starts at 1. At some point of time it is at 2 but it's not collided with the platform. After the collision there is a new velocity which both those, the platform and the mass attain, and then eventually it ends up at 3, and this is the y we're interested in. So we'll do it in parts. So first, motion from 1 to 2. Okay. Now there are multiple ways of doing this. You can use conservation of energy. Initial kinetic energy plus potential energy is equal to the final kinetic energy, assuming that the datum is down. Or you could just use motion under gravity, right? So I'll use the second one. V square is V0 square plus 2 GS. Okay. The velocity at 2 is unknown. The initial velocity is 10, so 10 square plus 2 times this is FPS, so 32.2 times 3. Okay, the velocity of the mass just before it hits the platform is 17.1 feet per second. It's clearly increasing, right? So this is fall under gravity. So motion at 2. So this is, so when the particle hits the platform, it's a plastic collision and the momentum is conserved. So what I'll do is I'll use conservation of momentum. So M A V okay, let me call this V2A so that I can use it here. V2A equals the final momentum, which is now MA plus MP for the platform. Will have a common velocity. I'll call that V2 prime. Okay. So the mass is 5, the velocity is 17.1, the new mass is 5 plus the mass of the platform is 1 pound, and V2 prime is an unknown, so V2 prime is equal to 14.25 feet per second. So you can see that because of the collision, the velocity of the combined mass and platform will actually decrease. Now here we make an assumption, which is the time for collision is so short that the platform is not going to move in that short amount of time. So it collides but doesn't move down during the collision. Once they achieve a certain speed, the common speed V2 prime, now it's going to move under gravity. So that's a fair assumption as long as the time for collision is very, very short, and that's usually the case. Okay? And we also assume that this particle, this mass, doesn't bounce off. So motion from 2 to 3. So from motion from 2 to 3, I can use the conservation of energy because there's no losses and there's only conservative forces, and moreover you're asked to find velocity as a function of distance. Okay, so T1 plus V1 equals T2 plus V2. The initial kinetic energy is half ma plus mp v2 prime square plus the initial potential energy. Now I'm going to assume that the datum is right here, which means that the potential energy is ma plus mp times g times y plus the energy stored in the spring, which is k times, it's 1.75 minus 1, sorry, 1 minus 1.75, so it's 0.75. It's the same as what I had last time, equal to the new potential, new kinetic energy. It's 0 at 3, sorry, plus the potential energy is 0 because the datum was at that point where this thing is going to be with 0 velocity, plus the potential energy due to the spring, which is half k, and it's pretty much the same as previous. It's going to be 0.75 plus y. So this is what I had last time. Remember, it was 1 minus y minus 1.75, which is 0.75 minus y. I have the same thing here, 0.75 plus y. I think it is minus y minus 0.75. That's right. Okay, so if you take this expression and simplify it, what you end up with is 200y square plus 294y minus 18.92 equals 0. So again, you'll get two roots. You should take the positive root. The positive one is 0.06175 feet. And something to note is that if you look at the previous answer, it's 0.0735. This is less than 0.0735. What's that? This expression? No, it's 0.75. Look at this. It's 1 minus y minus 1.75. So it's minus y minus 0.75. So when you square that up, you get y plus 0.75 squared. This thing is minus y minus 0.75 squared, which is the same as y plus 0.75 squared. Yeah, it remains the same. Is that, yeah, any other question? Okay, so thing to note is that this distance, displacement, 0.06175 in the second problem was less than the previous one. And the reason why it's less is only because energy is lost during the collision. If you had got more than the previous one, that would have been a wrong answer. What's the time? Any questions on this? See. Okay, I don't think I can do any of these questions. Maybe only this one. Let's try to do this one, and I'll let you go. Or do you want to do it yourself? I'll do it? Yeah. Okay, so. Okay, so due to slipping, points A and B on the rim of the disk have velocities shown. So a given velocity of B, velocity of A, velocity of B, determine the velocity of the center points C and D. So velocity of C and velocity of D is unknown. Okay, so what type of problem is this? What's that? Kinematics, right? The hint is, well, there's no mass given to you, there's no inertia, there's no gravity, and that's a sign that it's not a kinetics problem. So when you have a velocity, when you're given velocity of one point, told to find the velocity of another point, and there are two ways to do it. One is, there might be more, but two ways in which we've taught you. One is to use the instantaneous center. The other is to use the relative velocity formula. I'm going to use the relative velocity formula to do it, but you should totally try to do it using the other way, the IC. Okay, so relative velocity. So velocity of C is velocity of A plus velocity of C with respect to A, and this is velocity of A plus the velocity of C with respect to A is omega crossed with R C with respect to A. Okay, so that should be in your formula sheet. So let's stick a coordinate frame. Okay, velocity of A, as you can see on that figure, is 5 feet per second in the I direction. So 5I plus omega. Omega is an unknown. You don't know what omega is. So I'll write omega. I'm going to assume omega is counterclockwise. That way it's positive. Omega k crossed with the vector from A to C. So the vector from A to C is Rj. So R is the radius. That's 0.8 times the j component, right? This vector. So this is 5I. K cross j is minus I. So minus 0.8 I. 0.8 omega I. Okay, so I cannot find VC unless I find omega. So how do I find omega? If I can find omega, I can find VC. In fact, I can also find VD if I can find omega. So how can you find omega? So where did the 10 come from? You know the velocity of B. So we can try to find a relation between velocity of B and velocity of A using the same formula as before. So velocity of A is, this is VA plus omega cross RB with respect to A. So velocity of B, as you can see here, is 10 units, 10 feet per second toward the left or along the minus I direction. So minus 10I equals, the velocity of A is 5 along the plus I plus omega k cross the vector from A to B. Okay, the vector points in the positive j direction, and it's equal to the diameter of the cylinder. So that's going to be 1.6 j. So minus 10I equals 5I. This comes out to be 1.6 omega. K cross j is minus I, so that's minus. So what you have is an equation in I which has one unknown omega. So omega is minus 10 minus 5 divided by 1.6. That comes out to be 9.375. And since the sign is positive, it means that our assumed direction was correct. It was counterclockwise. So from that, we can put this here to find VC is equal to minus 2.5I. And what I have not done, and I don't have time for this, I think I'm out of time. So you got to find VD is VA plus omega k crossed with R. Sorry, let me write this as omega crossed with R D with respect to A. Okay, so this is to be done exactly like I did it. The only thing is you need to find the vector from A to D. Okay, the answer is minus 7.8 I plus 5.3J. Okay, I'll finish this up and post this. I'll post these things up, and I hope to see you tomorrow for the tutorials. It says in EB 3.04.30, 10 to 12.